Okay, I would like to give some information about mutual inductors. So let's get started. Number one, I'll be introducing the circuit symbol. So mutual inductor is actually a two-port, as you see, having left side and the right-hand side, which is called the primary and the secondary. And what is interesting is that now we have L1 in Henries, L2 in Henries, and well, for these two inductors, we have another component called the mutual inductance, as the name implies, M. Okay? So this is the mutual inductance between those two coils. First of all, what is the meaning of this? As we have said, this is just a two-port. In this two-port, we have this component placed. And what is the purpose of this component? And what is the physics behind of this component? Well, you will see that this component has lots of applications, very, very important electrical applications. And it is something extremely physical and important. Now, let's consider two windings representing this and that. Okay. So in this winding system, so what is this one? This is a high permeability medium. High permeability medium. Essentially, well, this is iron. Okay. You may think about it as like the iron core. So I have on this side V1, I1, on this side I2, V2, representing this. Now assume that this is not present at all, or I'm not energizing this second coil. So that means that I'm left with this L1. Okay. So typically, when you place an AC source over here, and let's say that there is a small amount of resistance over here, so this is an AC source. This will be creating, obviously, an AC current. And this AC current will be introducing a magnetic field. Well, magnetic field, which is produced by, let's say, right-hand rule. So we have right now this magnetic field, let's say, flux oscillating in this iron core. So, of course, there can be, leakage, magnetic field and so on across over there. Okay. Leakage that you may think about. So what is interesting is that now if I have an energized coil number one, some part of this flux or some part of this magnetic field is also intercepted by the second coil. Okay? So that will be related with this mutual inductance value M. So let's assume that I have a cross section over here. So in this cross section, this magnetic field is intercepted, as you see it goes through, and intercepted by this cross section of that iron core. So this is the iron core when you look at from this side. Actually, it's a three-dimensional object. It is something like this. So this is an object like that. Okay. Okay. So this is essentially cross section for that part. Cross section for this part. Now, what is important is that this magnetic field produced by the primary coil, coil number one, is intercepted. Its B field is intercepted over here, over this surface. Okay. So this is the definition of flux essentially. As the B field is passing through the surface, it introduces a scalar concept flux. Okay. Now, similarly, the B field introduced by this coil number one is also intercepted by itself over here. So this is called the self-inductance. So energizing coil is intercepting its own flux essentially. And then for this one, if I call this phi 1, total flux intercepted by coil number 1. Since we don't have anything like this right now, we don't have the second coil, we have the following: L1 times I1 of t. Why do I say total flux? Because we have lots of these cross sections over here. So every turn of this winding introduces a new cross section. You may think about it like that. It makes that, this region bigger and bigger every turn. Okay. So this is called the total flux intercepted by coil number 1. So similarly, I can write, let me write it over here, phi 2 of t. Okay. There will be a coupling over here. This is total flux intercepted by coil number 2. Now, this is not energized, so this is the flux due to the first coil. Okay. So we are introducing that one as M. This is this M over here times I1 of t. Now what happens if I introduce the second coil also? Now both of these coils are active. If both of those coils are active, now by the right hand rule, if this goes this way, now there is also, let's say, red flux or red B field right now. It's not the flux but the red B field. So this one is also producing another B field in the same iron core, and because of that, now there will be an additional flux over here. And this is essentially the same mechanism, creating this, B field across this, iron core. Okay. So now we say that for the second one, this is due to the mutual coupling, and I have L2 times I2 of t. Okay. Actually, this L1 flux, this equation, is the definition of the inductance. So assume this says that this flux, total flux intercepted by this second coil is, this is due to the self-energizing coil, and this is due to the other coil, and I have that. Now for this one, for the first one, when the second coil is also present, I have, the additional term. So the second coil, when energized, it creates this green B field, and then due to that green B field, there is some additional flux intercepted by the first coil. Now there can be an issue. So is this M is identical to this one? Well, essentially due to the reciprocity kind of reasoning, because it's a physical medium that can be constructed out of physical materials and so on, this M values are exactly equal to each other. This is some kind of a reciprocity kind of relation. If you energize this over here and measure it over there, or if you energize it from here and measure it over there, you should get the same value. And because of that, you should get the same value sentence. These two M values are the same. Okay, so that is the end actually. That is the end. Now, next we have Faraday's law. So what is Faraday's law? You take the derivative of this flux. So rate of change of flux is nothing but the voltage. Now we got this V1 of t is equal to L1 d dt I1 of t plus M d dt I2 of t. Similarly, if you take the derivative of this one, let's write it over here. Again, this is called Faraday's law. Rate of change of flux. This is V2, okay, is equal to M times d dt, this is constant, times the derivative of this one, I1 of t, plus L2 times d dt, is it I1, I2 of t, okay. So for the sake of our course, circuit theory course, actually we are starting from these two equations. So these are the terminal equations representing this mutual inductor whose physical construction is something like that. Okay? And we use these two equations just to represent a relation between, this relation between voltage and the currents of this two port. Okay? V1, I1, V2, I2. As you see, they are present over here. Okay. Now, how about these dots? Now dots are actually very important. Like, let's write this, dot convention. So what is the purpose of these dots, and why do we not have dots when we have like the self-inductances and so on? When we don't have, when m is equal to 0, we don't have these dots. Okay. So why don't we have it? Well, the thing is the following. Well, we have two winding possibilities over here. You can make this winding across this iron core or behind this iron core. So the first wire can be on the top, or the first wire can be at the behind. Okay. So if it's at the behind, due to the right hand rule, flux, this green flux will be going in the other way. Okay. So if this wire was, because of the right hand rule, it changes as you see. Now you see that we have two possibilities. Well, depending on this winding direction, there can be constructive or deconstructive fluxes. So they can be additively interacting, or they can be subtracting from each other. Okay. So that can be an issue. So the winding direction is also important, because if these two magnetic fields are cancelling each other, so we are getting less flux. So depending on this winding direction. So this gives another freedom, as you see. So these dots present that freedom. So that these dots are related with winding directions, and you may consider that these dots show that when the currents are entering over here like this, I1, I2 entering into the dots, okay? So they are creating constructive, let's say constructive flux, and that shows the direction for the constructive flux, okay? So if you move this dot to the other side, you may consider that the winding direction has changed. Winding direction has changed. It's like deconstructive. The B field is cancel. B fields introduced by these two coils are cancelling each other. So that is the purpose of those dots. So what else? Now we have achieved the terminal equations. We have explained this dot convention, and this dot convention is very important. Let me say it one more time. Current is, so this is the, as you see, inductor symbol. So I1 is entering into the dot, okay? So going out over here, entering in, okay? So we have V1, positive polarity, is aligned with the dot when current is entering into the dot. Okay. So similarly, I2 is entering into, and the positive polarity of V2 is aligned. Okay. So this is extremely important. Please remember that for one port, this is what we call the passive sign convention. So if you have a resistor, let's say some kind of a resistor over here, now if you define a mathematical relation between this voltage and resistance's current, let's say that Vx of t is Ix to the power 3 times 5. I'm just making this up. If we have something like that, now this equation is only valid, clearly, it is only valid when Vx, Ix is assigned like that. Again, current is entering to the plus terminal. Okay. So in both cases, as you see, currents are entering to the plus terminal, plus polarity. Okay. And dot is denoting this plus polarity essentially. So with this kind of convention, current entering to the plus, this is valid. This is called passive sign convention, as you know. This is an old topic right now for us, passive sign convention. So this time we have two ports. So for these two ports, now I have I1, I2, V1, V2. What is the convention for them? So the convention is, again, I1 enters to the plus sign, and due to this winding direction, I put the plus next to the dot. That is our, definition. In short, for these equations to be valid, for these two equations to be valid, I1, V1, I2, V2 should be defined as you see on the circuit symbol. So what else? Let's erase this part. Well, we have some examples already in your lecture notes. So this is like a supplementary lecture for the missing cases, let's say. So first of all, let me write this in matrix form. We would like to use these matrices. The reason is, this is like an upgrade of our knowledge from the scalar cases to the vector cases. What do I mean by that? Well, previously we had something like this, VL of t, L times d dt IL of t. So this is the scalar equation. What do I mean by scalar equation? So this is just a function. So this function is from real numbers to real numbers. Okay? So it's just an ordinary function. Similarly, this is also a function. So in other words, this is for any, let's say, t value, time value, it's just a number. But over here, you see a vector. Okay? Over here, you see another vector. And these two vectors are mapped by, if I write it like this is the L matrix. Let me use capital I for this, capital I of t. So this is my capital I, this is my L, this is my V vector, V of t vector. Okay. So as you see, now this equation, it terribly looks like the first case, the easy case. But right now, you can say that, okay, this is a function of single variable, obviously, from r to r square, okay, because it's a vector, okay. So also similarly for this one. Now you may wonder, what is the meaning of taking the derivative of a vector? Well, it's very simple. You take the derivative of every entry of this vector. Derivative of every entry. Well, this is the general picture. This is the special case right now. Now, depending on the m value, we may have different cases. For example, when m is equal to 0, you have two mutual inductors. Maybe they are very much separated from each other, and this coupling is equal to 0. Okay. So we have V1 is equal to L1 times its own current, V2 derivative, V2 is equal to L2 times derivative of its own current, and so on. So that is it. Now, again, you should see examples in lecture notes for some other cases. Now, I would like to discuss, first of all, a few applications of this, like in the old days. These mutual inductors, or let's say cores, were used. It's like a fun application. So you had a core like this. So this is called magnetic memory. So this is equivalent of your RAM in your computers. So in this magnetic memory, so you are energizing, because flux is conserved, you are either creating flux in this direction, so this is bit is equal to, so you are trying to store information right now. Bit is equal to 0, you are energizing this iron core, and there is this B field over here, you are creating this flux, and so on. And the other cases, again, you have this, you are energizing it such that magnetic field is in the other direction, okay? So this is bit, stored bit, is equal to 1. So this was the early day of computers. So you were storing information through this magnetic cores, essentially, that iron core. Okay. So you are energizing this coil such that if the produced flux according to right-hand rule, you know, if it oscillates like this or oscillates like that, then if you can read this, how you can read this? Well, maybe you have a second coil over here, and you are looking just to read this bit information right now. You should check which direction is magnetic field is present. You are putting a second coil, this is for the reading purposes, and if you see a positive or negative voltage over here, then you decide that, okay, bit is 0, or bit is equal to 0 or 1. But due to the losses in this system, because of these leakages and so on, even though flux should be conserved, there is always a loss in this medium, what is called the resistance due to the resistances or ohmic losses. So you have to energize these coils regularly so that this magnetic field in the core is not lost and so on as we wait longer and longer and longer. So like in some computer languages, you get an old ones like C, you get an error message saying that core is dump. You have an error, core dump. So when I was first seeing this message, it doesn't mean anything to me because core dumped. Core dump is, much later I have learned that it's a very old error message. That very old error message says that all of these memory locations are cleared. So how can you clear those memory locations? Now you want to, let's say, reprogram your computer. You are energizing them or de-energizing them. You are getting rid of this magnetic field by dumping this magnetic field or flux in this iron core. That was the issue. Core dump message was that you get an error and it says that, okay, like an old computer. So this error message still it comes up in, because it's like an inherited entity from the old computer programming habits. So core dump message, it's still appearing in many computer languages. Okay, this is a very early application. What is the main application of mutual inductors? Well, it's actually transformers. Well, that is the important application. But we should maybe study first, before the applications, power and energy relations. Let's do that. For the mutual inductor, well, power and energy for any electrical, mechanical, chemical, let's say component and system, they mean the same thing. What do I mean by that? Power is sometimes always measured in watts. Energy is always measured in joules, and it doesn't matter whether you have mechanical system, electrical system, and so on. Okay. So for our purposes, this is a 2 ports right now. How do you measure power consumed by these 2 ports? So it's the instantaneous power, because I have functions of time. Well, let me write this as P2 port. It is, again, by passive sign convention. This current is entering, as you see, let me make it longer, to the plus. Entering to the plus, okay? If that is the case, now this is called absorbed power. Again, passive sign convention. By these 2 ports, okay? Absorbed power is, the other components are sending energy to this component. Somehow, this energy is either dissipated or stored, whatever it is. That energy is transferred to that 2 ports. Okay. So as a function of time, this is equal to V1 of t times I1 of t plus V2 of t times I2 of t. Okay. That is it. So, but I want to write this one as in, because I like vectors. I1, I2 as a function of time. Let me write it better. Now you will see the application of, linear algebra a little bit. Not so much, but a little bit. So this is essentially called, an inner product. So I have a vector interacting with another vector, okay? Also called dot product, and I get a scalar value. Scalar means a real number. Okay. So how can I write this? Now for a 2 port, this is always valid. Now from this information, for mutual inductor, as a function of time, so let me write this as my current vector, and let me write this as my voltage vector. So current voltage, not the product as in the scalar case, but the inner product gives you power of this, let's say, multiport. Now this is I of t times B of t, but since I am defining these vectors as like column vectors, so I should be maybe using transpose over here because it's like a row vector. It's transpose of a, no, this is row, this is a column vector. So let me have that. I have this, okay? So then this is I of t transpose, but what was V? V is equal to L times derivative of I. So I have this matrix and derivative of I is present. So this is the end for the mutual inductor instantaneous power. So this is my L matrix. So that is it. Now here's a question. If on my iron core, let's say my iron core is over here. If I have 3 coils like that, not 2 but 3 coils, and 3 coils, coil number 1, coil number 2, coil number 3. What will be the change? The change will be, well, you have B field due to this one, blue, maybe B field due to this one, green, and let's say that B field due to this one, red. Now you have the superposition of 3 B fields and they will be contributing to the total flux intercepted over here, and there will be, let's say, coupling inductance M12 between first and the second coil, and this will be M23. Again, from the reciprocity reasoning, if you energize this, measure over here, or energize this, measure over there, you should get the same thing. And this is the reason that there is only one M23. There is only one value as the mutual coupling inductance of these, and there can be M13 like that. Okay. Again, there are 3 dots, things like that. Well, for our purposes, the only difference will be this L matrix will be, well, in this case, we have derived it for 2 by 2, but if you have 3 coils, now this L matrix will be 3 by 3. In other words, L1, L2, L3. Then I have M12, M13. So it will be a 3 by 3 matrix essentially. So all of these calculations are also valid for, let's say, 3 ports if you have a third coil over here. So only difference is that now you have a vector of 3 components, and you are calculating the dot product of them to get this, instantaneous power. So this equation is very nice. It's always valid. So this is the reason that sometimes we don't even mention the dimensions, because this is always valid, as you see, for all L matrices. Okay. So what else? Now this is, as I have said, power. Now let's go and try to get the energy So again, energy is like better. So what is the energy relation and what do you mean by the energy? Well, for the sake of simplicity, let's say that you have a box X, and this box X is absorbing some energy from outside world at the rate of, when you talk about the rates, energy absorption rate, it becomes power, okay? Maybe we should write this. Px of t is equal to ddt of Ex of t, okay? So this is energy absorbed by X at time in, let's say not at, but during the time interval, let's say minus infinity to, let's say, t, okay? Or let's do not include this, minus infinity to t. Okay, so energy absorbed by x during, from the start of this experiment at minus infinity up to that time. So it is a rate of change of that, okay? It's rate of change of energy. For example, if I consider a function, just like sketch this. So this component is, this is the absorbed energy. Somehow, at this point, you are calculating the slope. Let's select a good point. For example, this one, let's say. You are calculating this slope at time t is equal to tx. This is our t in seconds, let's say. And this is in joule, okay? So this is the tangent line. So then this is 1 px of t, which is ex's derivative, okay? Sometimes we use, these commas for derivatives and so on, but I think it's clear. It's already written over there. So this is always the case. Power, energy relations, it's not only valid for electrical components and so on, it's, as I have said, valid for mechanical, chemical, etc., for all. This is a general relation. And it's very interesting because you have a, let's say, electromechanical system, you have some motors and so on, so energy is always conserved. In other words, you calculate the electrical energy plus mechanical energy, maybe chemical energy, their sum is always conserved. So it's very interesting. So those very different fields are essentially communicating through this energy variable, etc. But for our purpose, it's currents and voltages. For the mechanical, maybe it's like the velocity, mass, etc. and so on. So we have things like that. Now, okay, we have remembered what this is. So if I take, this is equivalent to this one. Okay. So what is this? Again, this is energy absorbed by x during minus infinity to t interval. So actually this integral tells us that because, assume that, well, not from minus infinity, but let's say I start my experiment from 0. So from experiment time 0, my power is watts. It's 1 watt for a second. It's like 5 watts for 3 seconds. And let's say it's 0. All the way. This is 0 before, so I have this. So this is, let's say that I'm calculating this, or let me give it maybe a little bit easier. Ix of t. Ix of t, this is my x. This is my component x. This is my Vx, and let's say that I have 1 ohm over here, okay? So this is the current, well, from 0 up to, let's say, 5th second. So what is going on? So how do I calculate this? So what is the power of this 1 ohm resistor? Well, its power is I squared times R. But since R is equal to 1 ohm, it's just I squared, okay? So since current is constant, it's just 1 watt, 1 squared times 1. 1 watt for the 1 second interval. So rate is fixed for the first 1 seconds, and then you calculate this area. This area is 1 unit. So you say that, okay, 1 joule is energy is delivered to this resistor. And similarly, if you do this calculation, now the current is jumping to the value of 5. So I have 25 times 1 ohm. So the energy absorbed by this component has the rate of 25 watts. Okay? So now this 25 watts multiplied by 2 seconds So you are applying, this current for 2 seconds, 5 ampere current for the 2-second interval, okay? Then you get 50 joules also. For the rest, that is it. So once you calculate this integral, you see that from minus infinity, beginning of the experiment, up to time t, maybe 5th second, this is calculating the amount of energy absorbed, because this is the power at that time. If you sum up these power values, if you think about it this way, you get the total energy, because this is constant as you see, absorbed by this component. Okay. Sometimes we call this work. Why do we call this work? Because this energy is somehow, if it's like a resistance, I'm just spending so much energy and there is some work done, maybe I'm heating my home and so on by this dissipating, one ohm is dissipating some, let's say, heat. It's converting electrical energy to, let's say, heat and so on. So this is what we call work done is that much. Okay. So essentially, energy and the work, we are using them sometimes interchangeably, as you see over here. Okay. So these are the things that you know. Oh, by the way, if this function is not like this, for example, my current function is maybe somewhat more complicated, isn't it? It's not, a piecewise constant function as you see over here. But it doesn't matter because, this is the nice thing about calculus. You can divide this like into small, approximate the smooth function as what we call like a square staircase approximation. And if you approximate this smooth function with a staircase function like this one that we have seen in our example, okay, then you can again apply the same idea, and you can make this approximation by making these, staircase approximation or reducing the width of these rectangles. Let me call this h. Smaller and smaller, I can make it as close as possible. So then you have the definition of integral. Okay. So integration is nothing but summation, as you see. So if you know how to sum such things, calculate the area of the rectangles essentially. This is the same as doing this calculation. Whenever you are getting confused by the integrals, think about something very simple, like integrand is constant. So if the integrand is constant, you get the idea. Let's say 1 watt for 1 second, okay, 1 plus 25 watts for 2 seconds, so I have 50 plus 1, 51 watts at the 5th second or at the 4th second, and so on. Okay, now very good. So we have seen this energy power relations. So now my task is deriving this energy of the mutual inductor at time t. So this is the absorbed energy, one more time, over here. But the mutual inductor is something like this. So for this mutual inductor, P mutual inductor, tau d tau. Okay. So how should I calculate this? Now let me do this maybe over here one more time. Okay. Now, if I write this, so how do I mean by write? Let me write it in the long form. So let me calculate this one first. Okay. So I1, I2. Let's do this product. So L1, I1 dot. Well, I'm using I1 dot notation to represent this, plus M times I2 dot, M times I1 dot, I2 dot. Okay. So let me then write this in capital letter also, I1, I2. So what do I have? So if I have this, or not 1 over, so I have L1, I1 of t I1 dot of t plus L2 I2 of t. This. Now I'm doing this multiplication. So let's say this. I1 is multiplying the first element, L1, I1 dot. And I have I2 is multiplying the second one. So I have 4 terms, as you see. I as a function of time. I2 as a let me write this, I1. I2 as a function of time. So I put a dot over here. Okay. So let's check. I1 times this. So I1 dot times L1 present over here. I1 times Mi2 dots. I1 times Mi2 dots. Okay. I2 times this. I2 times, not very clear, but I2 times that is also present. So why am I doing this? Now I need to integrate this. But maybe I can recognize this as, well, 1 over 2 L1 I1 of t square. Because if I take the derivative of this, I get this one. Well, I should actually be more careful, but I should be writing this because this said integration with respect to tau, dummy variable. So I'm inserting dummy variables equal to t, dummy variables equal to minus infinity, and so on. Okay. Whatever the case, now for the first term, well, if I take the derivative of this, I get this term. So this is called antiderivative. So antiderivative result is correct. So at minus infinity, I'm assuming that all currents and voltages, everything is equal to 0. So this is the beginning of the experiment. So I'm not worried about minus infinity. So I'm replacing at the end, after this tau substitute by t, I get a result like that. Okay. So similarly, I get 1 over 2 L2 result like this. Okay. And how about this one? So this is m. So this is actually d dt. Is this? Am I right? d dt. Well, let me see. This is for the last one. M is present over here. I1 of t, I1 of tau, I2 of tau, d tau. Okay. So because this is derivative of the product, as you see, I1 I2 dot, I1 dot I2, and so on. Okay. So this is derivative of this thing with respect to tau, and I'm integrating it. Okay. So after this calculation, this term becomes, you differentiate this function, whatever this function is, and then you integrate it, you get the original function back. You get I1 of t, I2 of t. Okay? So this is what we have. Now the energy relation becomes then, one over 2 L1 I1 square, 1 over 2 L2 I2 square, plus m times I1 of t, I2 of t multiplied. Okay. So it's very interesting. Why I'm saying that this is very interesting? So this is the energy, absorbed energy by this mutual inductor. So this is in joules, okay, absorbed energy. So this is interesting for us due to 2 reasons. Well, absorbed energy in this interval only depends on the current value at the final time. That is it. So for example, if you have a resistor, do you remember we had a calculation over here with flat functions and so on, staircase approximations and so on. For the resistor, the final value of the current of that resistor does not tell us anything about the energy absorbed up to that time. But for the mutual inductor, because of this derivative relationship, as you see. Derivatives, and over here we explicitly see that derivatives and integrals, they somehow cancel each other, and the final value of these currents, I1, I2, so you only need the final value of the current. This is not very surprising, because in many energy relations, this is the conservation of energy related result, you get such a case, the final value matters. But please think about this. This is this thing, energy absorbed by this mutual inductor in this whole time interval. Also, I can write this as follows: 1 over 2 I1 of t, I2 of t, L1 m L2 I1 of t, I2 of t. Okay. So this is called, well, this is a very important thing, a quadratic form, okay, or quadratic product in mathematics. Why do I say it's quadratic product? I think it's very clear, because it's a quadratic in this current, in the other current. So this is essentially, different variables. I1 and I2 are different variables. This is current of the first coil, this is the current of the second coil. They can be, they have no relation. They may have no relation in between them, so they are independent variables. So this is in quadratic. This is a quadratic with the variable I1, I2. That is it. And only the second powers are involved. So the maximum power is the second power. So we have second degree polynomial, meaning that this is the name of that one is quadratic form. Well, that is it. Now, again, if you do this multiplication, you get this result, okay? But let's do not spend time on that multiplication for now. And let's think about the following. Now, if passivity, now if my mutual inductor is absorbing this much of energy, well, energy of the mutual inductor as a function of time. So a mutual inductor, let me write this, or any component, a component we have discussed in 201 for resistive component is passive if a component, let me say x, because we are discussing x, if, I think it will be clear, Ex of t, energy absorbed by that component in this time interval. So let me see, energy absorbed in minus infinity to t, okay, is non-negative. That is positive or zero. That's the meaning of non-negative. Then the component is, well, I have to be more precise. A component x is passive if Ex of t is non-negative for all possible current or Vx of t excitations in minus infinity of t. We call that component, the component is called passive. Again, maybe this is looking complicated a little. Now, if you have a component x, so you are making an experiment, and you are seeing that this component is absorbing up to time t, let's say 5 joules, okay? Now you said, okay, it's absorbing 5 joules, nothing wrong with it. Maybe it's a resistor, maybe it's not a resistor, who knows? But if you see that this component somehow absorbs minus 5 joules, now you are sure that this component is actually delivering energy to the other components. Now the question is, where is that energy coming from? Because this component is energizing the other components that is interacting with, let's say, okay? Something like that. So there are some other components. So if you see that this component at any time t, this component produces a negative valued absorbed energy, then you can say that, well, this component is delivering energy to the other components. Okay, so that's a big deal for us. Now for the mutual inductor, now we should check the passivity condition for the mutual inductor. Let's keep this, and let's erase this. Now the question is, energy of the mutual inductor is, at time t, is actually this thing. 1/2 I1 of t, I2 of t, L1, M, L2, I1 of t, I2 of t. Well, for the mutual inductor, we are very lucky in the sense that energy absorbed by the mutual inductor is totally determined by this final current value. So I just need to check this. Now the question is, can this be, well, negative valued or not? Or if this is negative valued, well, let me write it like that, positive or negative valued. Can this be positive or negative valued? Let me say it like that. Can this be, this is given, can mutual inductor absorbed energy be negative valued for any, input is currents, voltages, whatever it is, but at the end, if you do this integral absorbed, you get this. For any I1 of t, the final value is fixing this absorbed energy. So for the mutual inductor case, so I need to take care of, answer this question. Is there a value for which, I1, I2 values, once I do this product, I get a negative number? Can energy of this mutual inductor be negative valued for any I1 and I2? Well, again, this is, we need some linear algebra results for this, but let me say something about this. For example, case 1, let's say that m is equal to 0. When m is equal to 0, there is no mutual coupling. Energy of the mutual inductor is 1/2 L1 I1 square t, because this is equal to 0, you get a diagonal matrix, plus 1/2 L2 I2 square t. So case number 1. So mutual inductance is equal to 0. Mutual inductance is equal to 0. Okay, can this be negative valued? Well, L1, L2, if L1 and L2 are positive valued, which is the case in practice, unless it's like a very strange problem setup, they should be always positive valued. Now this can never be negative valued, so only condition is L1 is a positive value, L2 is a negative value, L2 is a positive value, this can be never negative. Okay, so this is what we expect. How about this, other ones? When m is not equal to 0. Case number 2. M is not equal to 0. Now, this is a little bit more complicated, but let me say something about these quadratic forms. For example, if you have a function like this, well, that function is 2, 3, 3, 4. X, Y, two, 3, 3, 4. X, Y. If I have a function like that, okay? Now the issue is, this is a function of two variables, as you see. So can this be, is it always positive? I don't know this, or non-negative, I should say. So how can I show that this is positive valued or not? So we are actually, forget about this 1/2 factor, or move this 1/2 factor, as a inside of this, middle term, okay? Now you have, if you do this product, you have 2x squared plus 4y square plus 6xy. So this is my function. So this becomes almost like a calculus problem. Is this thing always greater or equal to 0 for all xy? Okay. That is the question. So how can I check this? So we need a way of checking this, but I don't know how to check this one because my knowledge is limited to from high school to functions like this. For example, I know how to check this one. 4 square 3x plus 5. Okay. I'm just making up this. So is this always positive valued or not? Well, how do you check this? You say that, okay, if this is always positive valued, it shouldn't have any real roots, isn't it? It shouldn't have any real roots means, b square minus 4ac, b square minus 4 times 5. If this is negative, indeed this is negative, okay? So we see that this has no real roots. If it has no real roots and if this coefficient is positive, I know that, okay, this is a function like that. This is f of x, function of a single variable. It's a function like that. It's taking the value of 5 over here when x is equal to 0 and then, increasing, doing something, okay? Well, maybe we should sketch this a little bit more carefully, but maybe something like this, okay? It takes the value of 5 over here and so on. Well, we know function of one variables, but how about function of two variables? Now I have the same problem, but this should be valid for all xy. So how can I check this? So how about this idea? Can I check this around this x-axis? Or around the x-axis, I'm very happy, 2x squared. Because y is equal to 0 on the x-axis. This is satisfied. I'm happy with this one. This always, meaning that this always greater or equal to 0. So I can check y-axis. But the thing is that this is supposed to be greater than equal to 0 not only on the x-axis, y-axis, but on overall possible values of x and y. So now the question is, given an xy point, is it above this? This is z. Is it above? It should be above according to this, if it is passive. Okay. So given this, how can I check this for all possible points? Now, right now I have checked this x-axis. I have checked this y-axis. So what did I see? Over this y-axis, I see 4y square kind of behavior. Okay. Over this, I see this. Over this x-axis, I have 2x square kind of behavior, and so on. So what should I do? How about this? Can I check this? Well, fxy, but I want to substitute instead of x, now 1 times t. Okay? So what's the meaning of this? X is equal to t, y is equal to t. So I'm right now checking a diagonal, as you see. So x is equal to t, y is equal to t. So I have 2 plus 4, 6, 12 t square over here. Because this means that x is equal to t, y is equal to t. Substitute t square, 12. Oh, okay. So on the x is equal to y in this sketch, it is positive on this x-axis. It's positive on this. It's also positive on x is equal to y. So do you think this will end? So I'm checking different directions, as you see. So do you think this will end? I need a better method of doing this. Well, this will end if and only you can find a counter example, because it says that this should be always x and y. For all x and y, this should be greater than 0. Now, how about this? Now I'm checking this fxy for, let's say, the xy pairs. What was this? Minus 3, minus 3, 2. Times t. So I'm checking right now in this direction, minus 3, 2. Okay. So what is the meaning of this? Instead of x, I'm writing minus 3. So this becomes essentially a function of a single variable, as you see. Because I know how to check function of single variables. and this is equal to 2t. Let's check this. So this is 9, 18. This is 2t. This is 16 plus, what is this, 16? No, this is 4 times 4, this is 16. Okay. How about this one? I have 6t square for this one, minus 36. Oh, I get, this is 34. So I get, as you see, minus 2t square. Oh, I see that. So if this function is evaluated at along this line, or if this function is evaluated at minus 3 and 2 points, or minus 6 and 4 points, okay, at that point, minus 6 and 4 points, then you get a negative value over here. So this tells us that now this one, this function, this condition is not satisfied because I have found a counterexample, minus 3, 2, and whole line, okay, scaled version of minus 3, 2. So this gives a negative value. So as you see, for the mutual inductor problem, if you go back to this, now we have a big problem. How do we handle this problem on the passivity of this mutual inductor? Luckily, this is a topic very well studied. So in linear algebra, so let me write this, x, y, let's say L1, L2, M, x, y. If it is greater or equal to 0, this is said as this matrix for all x and y, L1, L2 is a positive semi-definite matrix. Okay, so matrices satisfying this condition, they are called positive semi-definite matrix. Of course, this is not limited by 2 by 2 matrices, but for our purposes, for this example, it's this. So positive semi-definiteness check is, in this case, L1 should be greater than or equal to 0, L2 should be greater than or equal to 0, and determinant of this matrix, let me call this L matrix, determinant of L should be greater than or equal to 0. Okay, so this condition should be satisfied. Determinant of L, let me write it over here, L1, L2 minus m square should be greater or equal to 0. Now we have condition number 1, condition number 2, condition number 3. So we have these 3 conditions. So it says that if this is satisfied for 2 by 2 matrices, this is called a positive semi-definite matrix, double-sided arrows. So this means that these 2 statements are equivalent, and this is also equivalent for this, and this is what we want. So if my mutual inductance matrix satisfies these 3 conditions, I haven't derived this, then we say that this is a positive semi-definite matrix and this is a passive mutual inductor. Okay? Well, we expect all mutual inductors, because these are like just simple copper wires and iron cores and so on, they shouldn't be generating any electricity. They shouldn't be energizing other components, isn't it? So we are expecting them to be passive all the time. Okay? But we see that because of that physical expectation, there is a constraint on this, L1, L2, M values, and so on. So let's check our earlier example, like this example, 2, 3, 4. Okay. So let me call this A matrix. Okay. So the question is A positive semi-definite? It is not actually, because we have seen, the following: minus 2, 3, A times minus 2, 3. This was equal to, I think it was like minus 2t squared, isn't it? when t is equal to 1, I get this, minus 2. So it is not. Answer is, we know the answer. No, it's not because of this example. Okay, because I have found an xy point, minus 2, 3. Okay. And for that one, I get, let me see, minus 3, 2. Oh, you're making a mistake. It turned out to be, let's check. This is 4, 16. This is 9, 18. Okay, I think it's correct right now. Okay. So here's an example, minus 3, 2. For this one, if you multiply from left, from right, you get a negative value, so this is not positive definite. So let's apply these checks. So this is, let's check, let's use these conditions. Use positive definiteness check conditions. Number 1, L1 is equal to 2, greater or equal to 0. This is satisfied. Number 2, L2 is equal to 4, greater or equal to 0. This is also satisfied. Determinant of this matrix, determinant of A, well, this is my A right now, is 8 minus 9. Oh, this is equal to minus 1. And it is not greater than or equal to 0. So this is not satisfied. So this was the reason. So definiteness checks gives us the result. Okay, so one last thing, and this will be the end. So these positive definite matrices are very important, as you see, because they are related with energies and so on. Now, how can I show that this is the, these conditions are correct? So this is like a mini proof for the conditions for 2 by 2 matrices. Okay, so actually, if you think simple enough, if you can think simple enough, proof becomes obvious. You shouldn't be, thinking complicatedly. Now the question is this greater or equal to 0 for all xy pairs? Okay, for all xy pairs. And my conditions are this, but I think you can remember the determinant condition. So how can I do this? Well, we have tried some vectors at the beginning in this example. Well, it wasn't very easy, trial and error, it wasn't very good. But how about this observation? Let me pull this x out of here, okay? Let me pull this x out of here. So if I pull that x out of there, I have 1 y over x. This matrix, L1, M, L2, x, 1, y over x. Am I right? So this is equal to this. There is no change up to this point. So let me call this, since this is valid for all xy, their ratio, I will call this ratio alpha. So this is equal to x squared times 1 alpha L1 M L2 1 alpha. So if this is correct for all xy, it should be correct for all alpha values, positive or negative, isn't it? So how can I check whether this statement is always positive or not? Right now, this is, I can divide by this, whatever the x square value is, I can divide by it, provided that it's not equal to 0. Or stated differently, this part does not hurt me at all because this is always non-negative. So I should check the sign of this part essentially. Can this be negative valued or not? Okay. But I know how to check. This is a function of one parameter is just alpha. Okay. It's just alpha because right now I have fixed to this, first entry to 1 by just taking out of this bracket. Now, if let's erase this. If I calculate this, I'm going up. So I get L1, let me use black color. So I'm just calculating the second bracket. Let me indicate that second bracket by this. So this is L1 plus 2 alpha m plus alpha square L2 square. If you calculate this second bracket, you get this. Well, alpha square L2, 2m alpha 1. If you think about it, why this is the case, you get this. Now the question is, okay, I have in my first bracket, I have this x square also. Now the question is this equal to, greater than or equal to 0 or not? Now I know how to, it's not, there is no square over here. I know how to calculate, this is a function of one variable, is this greater or equal to 0 for all alpha values. Okay. Now you calculate the determinant, the thing that we have said. So this is always non-negative, provided that it doesn't have any real roots. The condition for not having real roots is, we are almost done. Discriminant b square minus 4ac. b is 4 alpha square. Oh, sorry. b is, well, this b is 2m minus 4 times AC. Okay. So if this is negative valued, we are done. So we have, this is then m square minus L1 times L2. It should be negative valued. We are done. Okay. So the condition for positivity, passivity, you may say, is this condition. We have this. And this is equivalent to determinant if you multiply this by minus 1, L1, L2 minus m square. Okay. So this is equivalent to determinant. So this is a determinant condition. Determinant is determinant of this matrix L1, L2 minus m square greater than or equal to 0. Okay, that's all I would like to say about mutual inductors. See you next time.